Okay, so it is my pleasure to introduce Professor Jesse Thomason from USC. Prior to that, he was a postdoc at UW, which is where I was. And at the time, when I started my postdoc before him, and so Luke Settleware came up to me in the hall, and he said, I'm thinking about getting a postdoc, and I've been talking with this Jesse guy, what do you think? I said, please God, please hire Jesse, yes. That's gonna make everything in my life better. And so he did, thankfully, and there's a whole line of work that has come out since then of us working together. One of my personal goals is eventually to be his most cited co-author, and I haven't quite gotten there yet. Prior to UW, he was working with both Peter Stone and with Ray Mooney so he was literally sitting directly at the intersection of a language lab and a robotics lab. And then that's something that he's building himself at USC as well. Being able to sit at that intersection, it's obviously an intersection that I care quite a bit about. And my one little sort of side additional comment that I'll just add for students in the room is that what happens as you sort of progress through this career is that you're looking for all these people that you can work with, that you can collaborate with, but it starts off as papers and it becomes much bigger things. So for example, when you have to senior area chair a conference or something like this, and you want somebody that you trust, and so then I can go and be like, Jesse, please do this with me. It's the only way EMLP will work this year. And
that's it. That's where that sort of red is. And I apologize to all of my colorblind.
and so
Sorry.
No, you're good. And so I would think as you sort of are collaborating with everybody and you're sort of building all of these relationships mature and build into bigger and bigger things. And so it's very useful to have all these people whose research you trust, whose judgment you trust, that you can then rely on to help sort of build out the community that you want to see the NLP turn into. And so with that, Jesse.
All right, thank you, Jonathan. I want to check real quick, can people hear me? I don't want to stand over there, but I will if I need to. Okay. That was a really poetic way of framing the fact that Jonathan can ask me to do service requests and I can't say no to them. So I'm Jesse. Given that intro, I think I can probably just jump right in. I want to go back 5 years to 2018 and make I feel more and more comfortable every year making this argument that this is probably close to what was one of the states of the art in language and robot interaction for humans in 2018, right before everything exploded with BERT coming out in natural language processing. And I just want to give a picture of what interacting with a robot system using natural language required 5 years ago. And then we'll reflect on what's changed and what hasn't changed and how we can inform our future research questions given that information. And hopefully I have sound, but I'm not going to touch the computer again for fear of it locking. So if I don't, there are subtitles. Sounds like it.
What should I do?
Oh, okay.
Move a rattling container from the lounge by the conference room to Bob's office.
Does rattling refer to the property of an object?
Yes.
Does rattling mean the same thing as empty?
No.
I'm still learning the meanings of some words. Show me an object you could use the word rattling when describing, or say none of them.
Watch.
I am getting the objects on the table and you focus. Okay, I see them.
This one?
I see. Show me an object you could not use the word rattling when describing, or say all of them.
Watch. This one.
I see. Show me an object you could use the word rattling when describing, or say none of them.
Watch. This one.
I see. Thanks. Now back to business. You want me to move an item from 3514 to somewhere?
Yes.
I should move something from 3514 to 3510.
Yes.
Okay. So now it's going to make the delivery, and I'll talk over it while that happens. But I will say, I know this is LTI, but if there are any of you that work with hardware, it's been 5 years, and every time I watch this video, I still get anxiety that the demo is going to fail. This is all one take. Took a lot of shots to get it, but it's one take. So we deliver the item. Our postdoc helper is going to shake it and verify that it does in fact rattle. Okay.
Thank you.
So there's a lot of words we could use to describe this interaction. Tedious comes to mind. The code is tedious too. So what all components go into this thing? You can see the microphone up here. We're doing automatic speech recognition. So this is not a text-based system. It is actually taking in the speech that I utter, transcribing that, and then doing some reasoning on top of the speech. So if I say, move the light mug from Bob's office to the west middle pod, it takes in my speech signal, turns that into tokens, takes the tokens and feeds them to a statistical semantic parser. This is a logical form representation saying I have to find an object that is both light and is a mug. I have to find an office owned by Robert. I have to find some office that is west of the pod in the middle, and then do some relocation command from one location to another on that object. So we've got a sort of semantic formalism that defines the things that can be done by the robot. And then you saw in the video that we also have the ability to learn a couple of new concepts. This is not an entirely fixed ontology. If we see a new word like rattling, we can use part of speech detection to say, okay, this is an adjective. I don't know what the adjective means, but I have to assume it applies to an object and sort of learn this classifier on the fly. And to learn the classifier, we have to know which objects are positive and negative examples. So we've got an object instance recognition method by which we're taking this camera, looking down at the objects, and then figuring out which of the objects it is in a sort of closed domain of possible objects it could be. So this is a very closed world sort of framing. There's 30 possible things the robot knows can exist, and if it's not one of those 30, we're out of luck. All those objects are pre-explored through a series of arm behaviors. So they've all been sort of played with, pushed around, picked up, dropped, and then we record information from the arm's haptic sensors, proprioception, and audio, as well as the video recordings while doing them to extract features using old school methods like fast Fourier transforms, feature histograms, visual vocabularies. We did very edgy. We used penultimate VGG features for some of our visual representations. Actually not very valuable when you have 3 examples, but you could try. A reviewer asked for them, so they're in there. So we use a word level SVM classifier So again, old school to figure out what a word means. So if I want to know what squishy is, I can do something like show me some things that are squishy, show me some things that are not squishy, and then learn separate classifiers for each of my sort of sensory spaces. So if I'm pressing on something from above and getting haptic feedback from my motors, that is actually how I can tell if something is squishy, by squishing it. So I can build a pretty decent classifier with this like very low resource method. If I look at the color of an object, that doesn't tell me whether something is squishy or not, but it's 2018. There's no other way for me to have the intuition that this word happens to refer to tactile properties of an object as opposed to visual properties. Then we do grounding, old school denotation. We've got our logical form that we're looking for something, for example, that's both heavy and a mug. We got to look over our domain of discourse of all possible objects. Here I'm just looking at 2. Applying our predicates, which are these learned classifiers, to every one of our object feature representations, getting some estimate of whether or not we think that word maybe or applies or doesn't apply, taking our logical operator to union these things, and then getting a distribution over confidence on our objects that this word is actually what applies to it. And so we've got this big sort of symbolic statistical method for turning a simple utterance like, you know, heavy mug into an actual denotation of an object from some closed set of small objects we might be talking about. It feels like overkill. And it's still very hard to do. We've also got a closed set of tasks. There's like a certain set of things this physical robot is capable of doing. The arm can grab cylindrical objects and the base can move. That means we can move places, deliver things to people, and move items from one place to another. I think one thing that is cool here still, even though the rest of this technology has been totally supplanted, is the fact that we can do a little bit of continual learning between the dialogues. We've got this bit where if we see a word we haven't seen before, because we're using an old school statistical semantic parser, we can say like, if we ultimately understand the denotation, like what office we're talking about when we say Bob's office, we can reverse engineer that and say, okay, that means that this word Bob must be a paraphrase of Robert, which we might already know from our role-based system or training data. And you saw we can sort of live learn new adjectives, right? We can learn what can or long or blue or rattling mean by asking for a couple of examples and refine those when new users come in by asking for more examples. So this part's fun. But this isn't really the way that we do any of this anymore, right? This is a slot-based information gain dialogue system. There's some Q-learning, not deep learning, for doing slightly better dialogue. There were neural networks, like I said. They took the form just of like penultimate VGG features, and at the time it felt very edgy and weird to do it. They were like hard to store in memory. It doesn't make a ton of sense to store all the VGG information on the robot in the first place because it takes up so much space in RAM. And we could do synonym hypotheses. You saw in the video, we hear rattling for the first time, and the best case scenario is that's actually a synonym of a word we already know because then we don't have to learn it again. But it's not, right? I think it asks for same thing as empty, which is a word we do know. They're at least both sound words, but we use word2vec there. Again, old school. So this is good old-fashioned AI, right? There's some statistical methods in here, but this is largely a symbolic pipeline. And this isn't the way that we do language for robots at all anymore. The space has become much more crowded than it was when I finished the PhD. You'll know the name Carol Hausman. This is one of a USC grad who's now one of the higher level researchers at Google Robotics. He recently had a chat with him and he was like, oh, you're Jesse. You were doing RoboNLP before it was cool. And that was fun, but also it means RoboNLP is cool now. And it's cool because we have large pre-trained models that have made a lot of the problems that this like hand designed system was solving much easier to get around. The barrier for entry is much lower. I trace this application to RoboNLP back to grounding language in play. This is a paper from Corey Lynch and Google from 2020, maybe, where we've got demonstrations from people and annotations of those demonstrations. Because these are people who had not worked with language before, they think that annotating information is called hindsight replay. It's data labeling. We've been doing this for a long time. And we can basically embed trajectories of robot behavior and language describing that behavior into a common space. If we embed it into a common space, that means at inference time, when we get a new language command, we can effectively do nearest neighbor retrieval to figure out what behavior sequence that language command corresponded to. Again, I know this is LTI, but in the reinforcement learning robotic space, they're often totally fine with test time inference being the exact same tasks as training time with like a little bit of variation in object positions or world state. So this is like very fun for them, that you can basically retrieve stuff that humans did to solve a problem using language and then solve the problem again, even if the problem is like slide the block to the left. And then recently as this summer, we see things like the robot transformers. This is the RT2 architecture. It uses basically the same underlying ideas of embedding language and trajectory and vision into the same space, but now with the ability to do closed loop control, where we start to move, see what changed once we started to move about the scene, and then condition our next actions based on what we're observing so far. And we've moved from sort of just neural network encoders to using transformer decoder architecture for everything. Encode the language, encode the vision, encode the actions, all using this like centralized general purpose transformer system, decode action space. Uh-oh. Did it die? I think it was charging.
Your screen's blank.
Huh. Okay, sorry. Okay, thank you. And then in the space of human-robot interaction, we can also start using language to affect change in the way that a policy is executed. So here we've got some work from Anka Dragan's group on giving an initial command and then refining it somehow to change the policy a little bit. And all of this is enabled by the fact that we now have fairly robust language encoders, right? We no longer need to have a sort of closed vocabulary set of words that we know how to recognize and that we know the meanings for. We can actually at least get some nearest neighbor information for a much wider set of vocabulary. So, old school, automatic speech recognition, semantic parsing, pre-exploring and registering objects, word-level SVMs, closed tasks, have largely been supplanted by various forms of neural methods in the last couple of years. So we've got large language models instead of semantic parsers. T5 is super good at this. Vision and language pre-training, like clip methods, can largely supplant object representations. And then we can build world models end to end by things like concept fusion is a nice example of building out an entire sort of 3D map of a world, like a small house where we've got objects annotated with visual features, audio features, and then there's speech recognition, which I'd argue for the most part in robotics and natural language processing is still ignored, except for the handful of groups that are actually really targeting speech as an application domain. So what do these large models give us? Open vocabulary feels like the biggest thing to me. Like when we're writing a statistical semantic parser, you're basically saying like, I'm gonna hand annotate 100 to 1,000 examples of ways that I think a person might convey this like symbolic information. And by and large, we can now take that training data and generalize to any way of saying that language. Like this has been the huge boon to me, especially in semantic parsing. And we can also do zero-shot understanding of neighborhoods now that we have large-scale joint embedding spaces for language and vision. Clip is the go-to example again here. Yes, biases, societal harms, et cetera, do 100% exist in Clip, but I also don't have to teach an SVM what red means or what like something being full versus empty mean visually. I can basically take the Clip score between language and an image and get a pretty good approximation, zero-shot, just off the shelf without having to start from scratch. So again, getting 3 examples from a person of what rattles and what doesn't, tedious. It'd be great if I could just form a hypothesis and have an initial classifier we work with. And again, for this semantic parsing bit, this means together with having good ways of rephrasing a command and understanding it, this means pick up the apple, grab the red fruit, lift the left object. If we've got a nice sort of clip-based representation of our world and a language model encoding our underlying intent, we can basically zero-shot understand these things with a model like SayCan or the language and play approach. And we've got nice learned representations of different kinds of input now. When I wanted to do speech recognition, I was pulling up, the CMU Sphinx speech recognizer off the shelf and, doing my best with a decoding lattice to get some plausible transcriptions of what the person might have just been saying. Now we can run Wave2Vec and get a literal embedding vector that we can do anything with. We could decode speech, we could port it over and use it for some downstream model. We've got a nice way of representing a lot of different modalities of information with efficient autoencoder-based learned representations as opposed to hand-engineered features. So I'd argue that large language models and large pre-trained models generally have made it much easier to specify the next thing an agent should do in a sort of open loopish fashion with an English text-based instruction. So keep this particular definition in mind as we think about things that we're not gaining from large pre-trained models. So you probably know this quote. This is also the beginning of my little abstract. I suppose it is tempting if the only tool you have is a hammer to treat everything as if it were a nail, is our quote from Maslow, and I'd argue that there is a very popular hammer right now. It is not, in fact, the only tool you have. I think it's hard to convince some first-year PhD students that that's true. It is not the only tool in the toolbox, but it is really tempting to treat everything as a nail now, right? Parsing, code generation, style transfer, annotating data, augmenting data. Robot walking patterns is my favorite one. Going from language to gait pattern for some reason. My favorite example there is when I saw it presented, the speaker noted that you actually can't reproduce the results anymore because GPT had updated since they made them. So what don't these large pre-trained models give us? Almost all of them first assume text input. I'm not going to text with my robot, right? Any robot actually operating in a lab space, in a factory, in a home, needs to have some more natural form of communication. We talk to each other, we should talk to robots. This is maybe a personal opinion, but I hold it as ground truth. We also still need to tie language to actual objects and behaviors that are possible for the agent. So CLIP is great. It gives us an amazing sort of prior on what somebody is probably talking about, but it will not enable us to actually learn new information about how a word relates to the world. Words like rattling, words like full and empty do have some visual connotation, but they're really not about visual features, right? They're about sensory information that we need some additional modality for. And then there's the classic example of a home robot needing to learn home language, right? Home words for like what a kid calls their favorite toy. It's just not ever going to be picked up by a CLIP model, right? And that's fine, but. So large pre-trained models that consider language plus some other modality are usually restricted to vision. I'll throw an asterisk in there because there is work, including from Dr. Bisk over here, on trying to like relax that assumption a little bit. There is stuff like concept fusion on throwing in audio modality too. But by and large, when somebody says multimodal, they mean vision is involved and also language is involved, right? The word is almost synonymous with the language and vision now, in a way that it was not 5-6 years ago. And language models that languages that, the use of language models generally discourage, I think, the use of languages outside English, right? Large pre-trained models do exist that are multilingual, but notice they tend to be multilingual language models, not language models trained entirely in a language that's not English, right? It's English and X, not just X. And again, mostly text. It's very rare for these things to think about any other modality outside vision. So if we think back to sort of like the purpose of language in the Greichen sense, I'd argue that extra-textual context should be used to inform language understanding. And this is sort of the thesis of both the talk and an entire sort of research thread I'm trying to follow in the lab. So what we say out loud depends on what we believe our interlocutor believes about the world. Right? This is just a sort of fundamental theory of mind assumption that we're saying something that we think can be understood by the person we're talking to. And we often assume that they're going to bring to bear reasoning and knowledge about the world that we are not saying out loud to them. So to simplify and formalize that a little bit, it's just that the language that we generate to communicate some intent, which I'll denote as A, is conditioned on our assumed mutual understanding of the world, S, with our interlocutor. So again, our utterance is just conditioned on both what we would like to convey and what we believe that the person we're conveying it to thinks. So when we're inferring an intent with a model, it just makes sense to condition on both of these pieces of information, on both the utterance that was said and on our assumption or estimation of what we think the state of the world, the mutual state of the world between the interlocutors was. Which again is just that the model should consider both the utterance and the state when trying to infer the underlying intent for language-guided robot applications. And large pre-trained models have enabled patching together that kind of information possible in a way that was much, much more tedious and long-winded in 2018 and before. So I'll talk about 3 directions my lab's been working on in this space. One is large language models for agent planning, for sort of high-level task planning in a symbolic space. Using them for speech recognition, and then using them for going beyond text in general for actually recognizing bits of sign language. So we'll start with agent planning, since this is sort of closest to home for me in terms of being a language-guided application. So in agent planning, if we wanted to think about our Maslow analogy, when we want to use a language model as a hammer, which I think has become sort of the fun dominant paradigm, especially for roboticists who want to try to use language models for something, they'll use a language model as a hammer and say, what if I threw out everything I know about robots and just used a language model instead? So if our intent is to get the agent to warm up a meal, and what we say out loud is reheat dinner. So our underlying intent, heat the meal, our actual utterance, reheat dinner. If we throw our end-to-end language model fine-tuned on some data maybe in context examples, I'm generally not going to differentiate these things. I know that LLM now refers to an entire family of material, so assume that I mean something sufficiently large scale that you think it might be fun to frame an entire problem as though this thing could solve it. So not always GPT-4, but often at least ChatGPT. One way this might fall out in the way that we observed in some of our early experiments is that the model will output a totally reasonable plan. You walk to the kitchen, you find a fridge, you open the fridge, grab some chicken, close it, find a stove, turn the stove on, find a pan, put the pan on the stove, put the chicken on the pan, right? This is not unreasonable. This would reheat dinner. But it's totally plausible that there's no chicken in the fridge. This is an end-to-end system. If there's no conditioning information about the kitchen, like, what are we doing? We're looking at a text distribution over the internet and saying that people eat chicken. It's not safe, actually, for a robot to turn on the stove. I know that this is still a thing people do in RL domains. I've seen Yonatan's fake kitchen. But, like, actually, a robot gripper should never go anywhere near the dials on the stove. I think that's a fair thing to say. And also, most robots can't hold 2 things at once. Like, from learning from people, it makes sense to be, holding a plate of chicken and grabbing a pan. Most of the robot grippers are just one gripper, one object at a time. And so we're actually failing some preconditions, too, in our planning space, because there's a mismatch between what a person could do and might tell another person to do versus what the robot agent is actually capable of. So if we consider, instead, using this language model as duct tape, we sort of just change the nature of the tool, then we can think about the state. So the state is that we have a shared world representation with the agent. So when we say reheat dinner, we assume that it knows there's no chicken in the fridge, for example. So if we duct tape together our ability to sort of like generate open vocabulary plans suddenly, which was just not a thing in 2018, with some world info to kind of restrict the nature of that generation, our hypothesis is basically that knowing what objects and actions are available, what preconditions are necessary, if we can give that information to the language model, then it can avoid some of these like hallucinated objects, actions that are unsafe, and these other things that we're worried will happen. And we'll show this quantitatively and qualitatively, but the upshot is that it's true. If we give information to the language model in the form of either our in-context examples or our fine-tuning data that say, here's the objects and actions you can actually do, here's examples of plans, then these plans become restricted by that local information. And there's been a couple pieces of work that basically all had this realization at the same time from a few labs. You might remember them if you were tracking this space like me last summer. One was to use language as a sort of next step heuristic to guide search. So there you use a sort of closed API of here's all the action object combinations you could possibly pick. Your goal is reheat dinner. What would you do next? This is the approach of stuff like SayCan from Google, basically simple language instruction that gets unpacked into a series of action object tuples. But they're just using the language model here as a re-ranking function to decide which one seems most plausible given sort of common sense reasoning baked into this thing. At the same time, there was the idea of using language as an API program. so restricting the generation by taking advantage of the fact that the GPTs and especially stuff like Codex is trained on code, and say like, if I make the plan look like code, it's a little bit more in distribution for the domain, and I can actually like have some code headers that say what actions and objects are available. So there were 2 bits of work that did this. One was code as policies at Google, and the other was the prog prompt from my lab through my student who is interning at NVIDIA. And then recently, there's been a bit of an orthogonal direction, which is to use the language model not to generate the plan, but to generate the goal specification in the symbolic language, which is to say what I'm going to give the language model is the fact that there is a planning formalism like PDDL or ASP. Here's how you turn language into goal conditions in symbolic state, and then use this thing just as a semantic parser. And as we've said, we're actually pretty good at semantic parsing with these large models, and then you can roll out a plan by just having the language model say what the goal should be, and then running a proper, verifiable planner that can go from start condition to goal condition. So I think these are all sort of in the same spirit of using the language model for a task that it's actually kind of good at by giving it information that it needs to do well. So I'll talk a bit more about prog prompt and give some examples of what we put together for that paper. So I'll play this more than once, but the general idea again is just to set up a task where we make the program or make the prompt look like a program. So we import actions, we list available objects. Play that one once more. There we go. List available objects, give some examples of what it means to accomplish a particular task where the function signature is the command, and then say, next function signature is going to look like this. Please generate me a little program that I can use, write an interpreter to turn into behavior in either a simulator or with a physical robot. So again, the large language model by itself can generate actions that the robot can't do with objects that aren't there. We can basically just restrict this by giving this sort of Python-looking prompt to the system that imports from a library of actions and lists available objects. So we're basically encoding the state of the world directly into the prompt. There's no sort of world state extraction. We're assuming a lot of information like that the world is fully observable. We know what the actions are. We know what the objects are. But if we had all that, here's how we could make a plan that actually conforms to the realities of the robot's constraints. So here's a bunch of small text you don't need to squint at, just to give a sense of what this looks like once we actually deploy it. So here's our list of actions, a bunch of objects, and a simulation. A couple of example tasks, and then a prompt, which is let's microwave some salmon. Then we roll out a big plan. We've got all our different little components of the interpreter. Not super interesting. The upshot is we can use the language model again and again with different prompts to do different pieces of the interpretation. And it means that we don't actually have to do anything in the simulator except execute the final plan. So we find some salmon. We learn things like if the microwave is closed, you have to open it first. That's basically baked into the common sense reasoning abilities of the language model. And we can make our plan. Walk to the kitchen, find the microwave, find the salmon, throw the salmon in there, heat it up, switch the microwave off. This thing, I think, goes ahead and does some bonus actions like putting the salmon on a plate that's not explicitly part of any of the insights or in context examples, but does fall out of the fact that it's a language model that does this common sense sort of task rollout. Y'all are also grad students, but I think at least profs in the room will think that this is fair. You can tell that I was not involved in the formation of this example because microwaving salmon is just not a thing you would think to do as a person who actually cooks and reheats food regularly. But if you're a grad student, I think you microwave whatever you've got. So this is also a nice example because if we, swap out the salmon for chicken and change this to make dinner, we'll get this rollout where we're actually making dinner with whatever food is actually available in the fridge. My favorite is if we do, if we put eggs and chicken in the fridge, we can do make dinner, and it'll select the chicken. Make breakfast, it'll select the eggs. It's got this nice, kind of feels like I can see what the language model is contributing here, right? It's bringing to bear not just now open vocabulary commands, but also a little bit of sort of common sense or social reasoning. Again, restricted to the training data, which is this very Western-centric English text, but. So we can now plan with underspecified language tasks, and this language model is giving us these nice biases about what's probably specified by that underspecified language. If I touch this, will it lock? No, it's okay. I think the connection might just be shaky. So the state information, again, is just giving us constraints from the, again, assumed mutual understanding that the person who gave the command assumes that the robot is going to have, that the robot understands make dinner is going to not involve scrambling eggs versus make breakfast will. And we can apply the same algorithm to a physical robot, so I won't show the whole prompting system here, but the command is going to be put the fruits in the box and the bottle in the, no, put the fruits in the plate and the bottle in the box. And this is for one where we have in-context examples that don't mention the fruits, they don't mention bottles or boxes. This is all sort of, can we do this thing even if we don't actually specify all of the low-level detail of how we connect objects to their words. So we sort the fruits in the plate, bottle and box, and we come up with these commands that accurately sort these couple of objects and then leave our distractor object, the drill, alone in the process. So again, in the good old days, statistical semantic parsing, closed fixed task set, object instance recognition, now supplanted in systems like prog-prompt with models like ChatGPT or Codex, allowing us to do semantic understanding and planning effectively zero-shot. I mean, there's the in-context examples, but these take very little time to put together. And we do that by taking our closed fixed task set and turning that into a closed action API. So we are still restricting what the robot can do. I think this has actually not changed too much. And now again, rather than having to do instant recognition, we're specifying directly here are the objects available to you. So we are assuming full state observability here, which makes, I think, in some sense, this weaker than some of the older work and then in modern robotics work that's actually doing state estimation. But we no longer have to hand program our semantic parsers, right? We can basically get these things for free out of large scale models. But we are typing. And I think largely speech is still an ignored modality in the space of robotic understanding. Where I do see ASR used for robotics, it is typically just off the shelf, either CMU Sphinx if the lab is older and Wave2Vec if the lab is younger, but we are just taking sort of the top hypothesis decoding and throwing that at the system as though it is the ground truth. So I want to talk about how we can apply this same underlying principle of swapping out our idea of language model as hammer for language model as duct tape to do a better job at tasks involving speech rec. So speech recognition, we're using language models as a hammer, very effective. I mean, I've heard the argument that Wave2Vec has solved speech rec, that this is now like a solved problem. I'd counter speech recognition as AI complete. I'll fight somebody on that if they need me to. But it's much better than it used to be, no question. So if our underlying intent is that we want to avoid microwave damage, so we're telling our agent what to put in the microwave while reheating that dinner, we could say use a ceramic plate. And again, this is not text anymore. I put it out here so you can actually see it, but we're assuming the user is actually producing a waveform now. So if we have our large pre-trained model, we're trying to go directly from audio to text. That'll be our hammer. So our agent just takes in the audio. But if we're giving this command in a kitchen, it is completely plausible that in the middle of our utterance, there's some large background noise that makes that audio a little bit more corrupted than what these things like Wave2Vec are trained on. Whisper is a good example of did we solve speech rec? Whisper is trained on podcasts with transcriptions. That means they're extremely clean. It also means if you give it a WAV file that is somebody quietly saying the word turnips, it will transcribe it as please like and subscribe. Not kidding. So it's clean training data. It's not really set up for the most part to deal with this kind of noise. There's sometimes data augmentation that'll try to throw this in here. You can make it a little bit more robust, but you cannot cover the space of adversarial audio attacks on your utterance, right? Which means that if we're going directly from audio to text, we are going to implicitly encode a bunch of language biases about what word is likely to come next, regardless of what the underlying speech signal is. And it's possible, we'll say, use a ceramic vase. Ceramic vase is totally reasonable bigram. It doesn't make sense in the context of putting it in the microwave. So this will lead to the robot doing the wrong behavior. Chicken in vase, vase in microwave. Hopefully the microwave doesn't close. If it does, God help us. So how do we switch this to a duct tape model? If we consider the state, which is that the person is assuming that the person they're talking to or the robot they're talking to has a shared understanding of the world, which means it should understand that in the context of being in the kitchen, we're probably not doing anything with a ceramic vase. We can tie that world info in to influence the decoding of our speech. So we assume the utterance is about the current working environment, and hopefully that helps us identify the correct words about that environment. And this should ideally lead to our better correct hypothesis of using a ceramic plate. So this is another place where there's a handful of related work. A.V. Hubert is one where we're jointly looking at both audio signal and, if you can squint at it, the mouth of the person forming the audio. So this is basically combining audio and lip reading as a sort of visual modality to understand. If you're familiar with things like the McGurk effect, this is known to be like a very important piece of our audio processing, is that we look at people's mouths while they're talking. It's also why when masks were very popular, we were all having trouble hearing each other suddenly, because we're used to sort of jointly lip reading while we listen. So I'd say here, we're taking advantage of visually salient phonology, that is the pieces of phonology that we can see. And we can't see all of it with speech, right? Like there's things in your larynx and your sort of glottal that you can't observe, but you can see a lot with the lips already. So use some image feature extractor as a backbone model, duct tape it together to get visually salient phonology that we use to inform our more or less end-to-end speech recognition. In another direction, if we consider the state as the image that we're trying to transcribe a caption for, so given some speech, you want to transcribe the speech, we know that the speech is about this image, then we can, again, just encode visual features and use those to try to recover missing words whenever there's damage to our audio. So this looks a lot like our setting. This is where we use our image feature extractor to understand things about the image about which the utterance is talking, and then use those visual features together with audio signal to do slightly better speech recognition. This, fun fact, is work from one of my students when he was here at CMU a few years ago doing his master's. So building directly on that insight, we consider the domain of Alfred, which I know a handful of people at least are familiar with from my one-on-ones today. This is just real quick, this is a simulated domain where we've got a big data set of language commands that correspond to behaviors in a 3D virtual environment. So we have the language commands here on the bottom and then the corresponding behavior here on the top across a bunch of kitchens, bathrooms, bedrooms, living rooms. And our idea is going to be to turn these language commands, which are written, into speech using a text-to-speech model, corrupt the speech from the audio signal. Since we know exactly the correspondence, since we're using this synthetic speech, we can get a one-to-one between where the words start and end in the synthesis, which means we can add our noising model however we want. We can delete the audio, white noise it, throw in a sound effect, and then compare a unimodal sort of audio-only hammer system that transcribes the speech. We'll use wave-to-vec to one that uses the information from the visual observation at the time that the utterance was produced for the navigation agent to do the instruction. And we can now evaluate not just did we get the right word, did we recover, but also does it matter? Because for some of the words, if we mess them up, we can still execute the task. We can actually go all the way downstream and see how important is it that we recover the right words to do the task correctly. I want to quickly mention, just because there's some profs in the room, this is work led by an undergrad who is the first author and is also applying to PhD programs. So if you're interested in this work, also maybe check this guy out. He's great. Really like working with him. Okay. So our approach is this. We take the input speech and run it through wave-to-vec. This is going to be our large pre-trained backbone. And we're going to duct tape that into state information. So we've got our wave-to-vec. We're going to learn our basic transformer decoder where we're starting our sequence. We want to decode words one at a time and just do a vanilla transformer decoder on our word-to-vec embeddings of the audio signal. But we're going to consider the egocentric view of the agent's camera at the time that the utterance was produced as context information for what we think the person understood the robot to understand at the time that the agent was supposed to execute the action. And for that, we can use CLIP, which is our nice free zero-shot language and vision relevant embedding system, concatenate those CLIP features to the underlying word-to-vec representation, wave-to-vec representation, and then decode our words one by one as we would anyway. But we've injected this multimodal information into the process. So we do an intrinsic evaluation just to see how well do we recover the words. So this is going to be a graph of, as we mask different kinds of words using this audio masking, our relative change in recovery, so how well we do with multimodal information versus unimodal only. So if we only mask nouns and we mask random 20% of nouns, we get this like little bump in recovery for heard and unheard speakers. So this is at training time, we've got so many synthetic voices. At testing time, we can use those same voices or new ones. And we find we get a little bit better recovery if it's also speakers we haven't heard before. So we get more robustness to variation in the nature of the audio if we also consider visual information. And as we increase the number of nouns that are masked, that difference gets more dramatic, and our recovery versus using a unimodal system obviously jumps up substantially as well, because there's less and less linguistic information for the unimodal system to fall back on. So it's wrong more and more often unless it can consider this visual info. Then we test doing all the words as well, not just nouns, to see like, are we only getting better because clip is like kind of bag of objects? And it turns out this effect like stays even if we are masking out random sets of words. It means there's probably some recovery happening in the space of actions at least as well. And we can try this in both scene environments, so environments that our wave-to-vec plus clip little decoder has trained in, as well as new visual spaces. So like, is it just that the visual information is being memorized so that even if it's an unheard speaker, we can still recover because we've like seen this kitchen before? And this is luckily not the case, though the effects are less dramatic if our clip encoder has not had a chance to fine-tune on the particular scenes that we're talking about. And we still get our recovery being slightly higher, especially for unheard speakers. And I mentioned we can also do an extrinsic evaluation. So we can take these transcriptions from either unimodal or multimodal ASR and actually run them on an agent trained to do Alfred. So this is the episodic transformer model, success rate on Alfred. So the dashed line is episodic transformer taking in the ground truth transcriptions versus multimodal in blue and unimodal in red. You can see that we get a slight improvement in performance over using the unimodal model, even in the downstream ability of this like already pretty noisy, getting 33% success on the whole task episodic transformer model. So in the good old days, again, we used automatic speech recognition off the shelf, maybe sort of word level SVM grounding. And here in this multimodal speech recognition, we're using wave-to-vec, so still our sort of like audio directly to text representation, but duct taped together to this language-informed visual representation from clip. So returning to what we're getting out of this, we've got this advantage of open vocabulary. With prog prompt, that means we can specify sort of underspecified goals, breakfast versus dinner, saying what is or isn't in the fridge. We can understand language and vision more easily with backbone models like clip, using in this embodied ASR example. But fundamentally, we are making things easier for English text-based instructions. And so in the last little bit of this, I want to note that the sort of proliferation of large pre-trained models in machine learning pipelines, I feel like it's causing a mode collapse towards treating English, especially text-based English, as an interlingua, especially things like chain of thought reasoning, a mixture of experts, what do they call it, Socratic models. But all of that is, let's use English as the way that models talk to each other and as people talk to models. Fine, but the research community speaks more than English. It seems kind of silly to treat English like an interlingua since we know that no languages are, and English is actually particularly hairy about ambiguity and weird morphology. So with that in mind, we also try to apply this sort of core principle of switching out our hammers for duct tape to the task of sign language recognition. So in this final space, we want to communicate an intent. We're going to communicate a single sign. We're going to focus on the task of isolated sign recognition. This is a person producing a single sign concept, and then the task of the machine learning model is to take in that video and recognize that concept. So this is a static frame of a video from a person producing the sign for computer. And a hammer approach, which is popular for this setup, is to take the video, the RGB, and just directly encode the RGB with a 3D CNN of some kind, some video pre-trained encoder, and decode the particular class from a fixed vocabulary. So there's very little training data for this, right? Anytime there's a sign language resource, it's because somebody, usually in linguistics, not in computer science, has sat down and said, this is important to me and I would like to create a data set, and the funding is pretty restricted, and so you get 1,000 examples 10,000 maybe. More if you look at sign languages across a bunch of different sign languages, because ASL is not the only one. It's not even really the most popular one in terms of like number of speakers. But it is the one that is used in the English-speaking country, which is why it ends up being the one that's focused on. So in our hammer approach, the models that we have tried often predict lettuce for this sign. Lettuce looks like this. This is also funny because it's sort of our dough. But you can see that the hand is kind of doing the same shape. The shoulders are a little bit in the same position, but it's a totally different sign. And to a person, these don't really look similar. So what's happening is these models are latching onto some spurious correlations in the training data and then using those spurious correlations to try to make predictions because they're actually sort of underpowered, right? They haven't seen enough to do a good job at this generalization to a new speaker wearing a different color shirt who looks different producing the same sign, right? So our duct tape is going to think about abstracting away some of those spurious features. And one way we can do that is to consider the pose of the person as opposed to their actual RGB video. So we can take RGB, run pose extraction, get positions of fingers, positions of skeleton like head, shoulder, and body, and then learn something either directly on the pose or with the pose as an additional signal. And this at least abstracts away what the person looks like as a way of producing a sign. So there are methods that do this. This one also, this particular one I'm referencing here also produces lettuce for our example of computer. But it does much better than using RGB directly for most of the signs. But the assumption here again is that the pose is sufficient to recognize the sign and that we know things that are not related to pose are probably not related to the production of the sign. We don't need to know what color a person's hair is to know that they're saying computer. So if we return to our assumption that we're looking for some kind of mutual information between ourselves and the person who is doing the recognition of our utterance. For sign language resources, we can think about the way that the resource was constructed. So in sign language recognition, the way the resource is constructed is usually, it's a single sign being produced for the purpose of education. So the state is that this is the social context is that the person who's producing this sign is doing so to teach it to another person. So they're articulating it clearly, they're articulating it well, and they're articulating the phonology, obviously. So if we want to remove more spurious correlations, we can basically tell the model, not only do you need to predict the sign, predict components of the phonology that we know are relevant for the meaning. So don't focus on the angle of the shoulders, focus on the shape of the hand. So we predict that predicting the labels of the phonology will regularize the model against more of the spurious correlations in addition to doing this pose-based approach. And this is very similar to what we mentioned earlier with visual phonology, right? This is basically lip reading, where we know that lip reading has something to do with the audio that's being produced. I mentioned for that we actually can't see a lot of the internals of the mouth. We can only get a little bit of sign from the lips. With sign language, you get the whole phonology, right? You're seeing the whole kit and caboodle of the production when you look at a person who's making a sign. So there's actually a lot more visual phonological information. It's all there. It's all visual. So what we can do is if we look at our test set, and I mentioned like we're going to misclassify computer if we use only pose information as lettuce. Here's the sign for sign. It's a fun, annoying example. Our pose-only model predicts problem for this. And you can kind of see why, again, here's a video of the test set for lettuce. Here's the video of the test set for sign. Hands are kind of in the same position. The fingers are kind of extended. So you can imagine why a pose model would be a bit confused here. But if we additionally predict phonemes from our joint positions, then we can basically use lexical resources because, again, there's not that much data about this in the first place. A lot of it is heavily annotated for the small number of signs that have information at all. We can say like phonemes that describe whether this thing is the word sign or the word computer include like the particular hand shape being made, the hand shape for 1 versus the hand shape for C, the location at which the sign is produced, neutral near the chest versus on the forearm, the sign actually being formed above the arm itself. And this is information that's still in the pose. So if we force the model to predict this information too, in addition to the sign, we discourage it latching on to spurious correlations in the pose. And this regularizes it so well that we actually get a big bump in performance and can get the correct sign for videos that look like these. So these are other training videos that look a bunch like sign, and you can see more clearly like this hand shape and location being consistent, this hand shape and location being consistent. So again, our assumption is that the sign is articulated crisply for the purposes of a demonstration. Would this work in something like continuous sign language recognition when somebody is signing fluently across a sentence? Probably not as well, right? Because then the signs start to blend together. People visually mumble the same way that we run words together as we talk very fast. But for this particular assumption that we're working with data that was produced for teaching, it works quite well. So we're going to look at sign recognition accuracy across a closed vocabulary for our test set, comparing just predicting the sign versus sign plus phonemes for an identical underlying architecture. That's a graph convolutional net over the pose points. And the upshot is, if we look at the entire test data, we get a much better performance on our test set with predicting phonemes as well. This is a statistically significant difference. And then if we look at only the test set of signs for which at training time we had phoneme labels, this is particularly like trying to tease out, are we just like memorizing the training data better by knowing what the phonemes are now? The boost is big when the test signs also had those phonemes. But if we look at the test set, the subset of the test set signs that we didn't have phoneme information for at training time, so we've only got it for some of them anyway when we're doing this regularization, we still get the boost. So learning the phonological information actually generalizes to entirely new productions for which we didn't have phonological information at training time. And this works across at least two architectures. The SLGCN, this graph convolution net, makes a bunch of sense. It's one of the close to state-of-the-art models. We can also just throw a vanilla transformer at it over the pose points and see that we still get these gains. They're still statistically significant. They still hold across this like phonological versus not split, but with a much weaker model. All right. So to quickly recap and cover thesis, yeah, what's up? So we're not looking at anything in sign generation at this time for sure. Yeah, this is just recognition. And again, it's recognition for the purposes of teaching. I think sign generation is its whole own very difficult problem, mostly in control space. Robots don't have this many fingers, and when they do, they're way too expensive for me. And most signs really require like pretty fine-grained finger flexion. I think that's probably way out of scope for me, at least for now. So to recap real quick and just wrap this back up, I want to reemphasize that I think that rather than using language models strictly as hammers, where we take in text and try to produce text and formulate a problem such that that's actually a general framing, we should consider the fact that language is produced for a particular context, take advantage of that context to do a better job with recognition, especially when that context is so easy to encode now that we have large pre-trained models like CLIP, like Wave2Vec, that can actually take in non-linguistic modality like audio and haptics and vision and turn it into something interesting for us to reason over. So we should consider the state in which an utterance was produced whenever we're trying to understand its meaning. And that observable state, again, can be in the form of vision, can be in the form of state information, it can be learned representations. And now what large pre-trained models have really done is given us the ability to patch those things together cheaply rather than having to hand engineer features for how we want to represent audio, haptics, proprioception like I was having to do 5 years ago with hand-designed feature sets. So we've done this with large language models for agent planning by putting our API definitions and objects directly into our in-context examples. For speech recognition, by extracting the features of the scene in which an utterance was produced to restrict the vocabulary that makes sense. And for sign recognition, by considering phonological information, given the fact that a sign's phonology is actually fully visible, unlike things like speech, where we can really only see a subset of the phonological production. End-to-end hammer methods are less data efficient. This argument was a lot stronger before everybody was using zero-shot methods for everything. I think it still applies because if you want to fine-tune something, you're stuck with LoRa or black box APIs where you're out of luck and just can't. Using only text is also easy. It's often very attractive for people to try because you can just throw the thing out of the box, see if ChatGPT can do it, and if it can, maybe you switch research problems or formulate some weird formulation of your set where your A and B are both text. But when approaching a new language problem as NLP graduate students, I mostly just want to encourage you to think about the space of what extra textual information the text input of this problem assumes, and how large pre-trained models might be able to encode that extra textual information to give you a little bit of a boost. All right, thanks for your time.
This is a really great talk, and I'm sorry because I have a little bit of a silly question. But since you're sort of like in the multimodal space and talking a lot about LLMs, I'm wondering how you think about like verbiage like foundation models and like your choice to use or not use language like that.
I don't think this is a silly question. I think probably the talk makes it clear that I'm not using that terminology. I've discouraged my students using it. This will be spicy. Trying not to be spicy. I think that it's uncool for a university that didn't come up with most of the concepts to say we're going to claim the verbiage and coin a term and then become the center that's allowed to do things in that space. I think it's lame. It's power grabby. They're allowed to do it because of that power. But I'll lose. We're not going to call them LPTMs, right? It's super awkward. I'll lose, but I'm gonna hold out.
Yeah, Professor Sherlock.
I have a question. How hard do you think this is going to be to try to go to a different language that has more richness associated with it?
More which?
Richness associated with, like, I mean, compared to English, as you said, it has all kinds of ambiguities and what have you. So, say going to Arabic or going to
Yeah, I think about Arabic, and of course everybody who thinks about multilingual that's not English thinks about Turkish, right, as the go-to, like, white space has useless character. I think it gets harder. It gets harder because, one, there aren't foundation models for Turkish, right? I mean, if somebody tries to train one, maybe, but it's never going to be as resourced as English, because English is the language that most of the internet text is written in because of the historical ARPA-like spin-up of the internet in the first place. I see a little bit of promise with multilingual models, but we know they consistently get worse as you move away from English. And the further away from English as the language family you get, the worse they get. I mentioned thinking that speech is AI complete. That argument is super easy to make for sign language. If people have a little bit of background in ASL, I can give just a small example of why it seems totally impossible to actually do good continuous sign recognition, which is that things like pronouns in ASL can be visually represented and often are. So if you're telling a story about a conversation that you had with somebody, you can denote them as a spot in front of you, and then you refer back to them. So you're talking about who is speaking as you sort of gesture at their location in your mental map that you've socially formed with the other people who are talking. It's a lot of mix of like iconic and non-iconic signs. So some signs will have like a clear sort of metaphorical interpretation, like if you're giving an example of a car crash, you can actually sort of draw the cars in the air, and everybody is visually watching to just see that description. We just can't computationally model that, right? I feel like this kind of thing is actually totally out of scope in an AI complete way. So for languages that are less resourced, I don't know about complex. I like the hypothesis that all natural languages are basically equal complexity. I don't know if that's true, but it feels right. But they can definitely be under-resourced. And for under-resourced languages, this whole paradigm of using language model as duct tape, I think, still holds, but it gets messier and messier. And I want more and more symbolic reasoning as we go that way.
So the reason I asked that, just to follow on, the reason I asked that question is there's the angle of complexity, which is about what's explicit and what's not explicit, the other implicit and explicit aspect. But the other aspect is the cultural aspect. So because you talk a lot about context, and context could be interpretable in different ways depending on the culture. So that's part of the reason I asked that question.
Yeah, I actually was having a conversation with a student earlier a little bit about this. I think the example was stove. Like the word stove refers to sort of the same semantic object in a Western versus Eastern country, but a totally different like apparatus, right, with very different operating function. And so, yeah, I don't know. I feel like I don't have a solution or even a research thread to begin to approach this problem, but it is increasingly bugging me that I feel like as a community we've just accepted that we're only going to use English and we're only going to talk about stuff as it happens in the US.
Thanks, this was really cool. I was wondering what your kind of like ideal interface between like vision and like embodiment and control, between that and something like a code model in the prompt work looks like. Like, do you think kind of like going through objects is going to be like helpful for generalization or things like that, or is it kind of like something that we need to do now because that's like the symbol space that code models or language models operate in? This is something we've been kind of grappling with too, and just curious to hear your thoughts on it.
Yeah, maybe I was talking to one of your students earlier too then. Thinking about the degree to which the fact that planning, reasoning, and sort of code-based representations for robot behavior has historically been done in simulation environments that are object-centric has probably strongly influenced the fact that we tend to reason about object-centric environments with sort of straightforward Gibsonian affordances of here's the actions you can do with this object successfully or not. And I suspect the answer is that it's actually influenced it a lot. Again, I don't have a straightforward solution. I'd like to think it's something like maybe we should think about using robots for weirder stuff. Right now, the applications, at least the funded ones, are largely restricted to factory manufacturing and kill chains for military applications. And those are object-centric. Sometimes the objects are people, but so I don't know. I think we have to get weirder with it. We could do that in simulation, maybe.
So first is a clarification question. So in the prompt paper, do you have to hard code any of the motions from the robot side? Let's say when the model predicts pick, how do you actually then be able to do that part?
Yeah. So the prog prompt system is assuming access to an API that will always succeed. That's an important one. This is an open loop plan, so it basically rolls out like, here's what you should do. If some condition like microwave is not open, is not met, you should open it first. It's got a little bit of like alternative planning, but it is open loop. It has to, the branches are pre-described, which means however we've implemented the pick and place policy, if it fails, it will fail. Like if we picked up the banana and dropped it, the system's not going to realize the banana's on the ground in this system. It'll just keep executing. For that one, they pre-trained a pick and place policy for like an object conditioned pick and place policy. So it knows what object it's going for and it accesses like a fine-tuned policy specifically for grabbing that object. So the success rate is quite high, but it means those objects are not novel to the robot. They're just novel to the API that is seeing the language. Does that answer the question?
Yes. And then the follow-up question is, I think pick and place is also not so popular, right? Because it can have different variations in the environment. Let's say I want to pick something actually from a very tiny box,
Mm-hmm.
then I have to use other like pick and place skills. So my question is, do you think that part can get help from language model, or do you think that part should get help from language model?
Did anybody do language-informed grasping yet? We keep wanting to. The problem is that like, we tend not to talk about fine motor control in language. Yeah, and so like, I remember we years ago at UW tried to play with like, can you use language to help inform the part of an object you should grab? And it feels like you should, but nobody says grab the mug by the handle. That's a psychotic weirdo thing to say, right? If you say that, you go back to Grecian pragmatics, that means something's wrong with some other part of the mug, right? That really specifically means you've got to get the handle. And so it just ends up not being written down that often. And I think for the same reason, like, grab the object that's in the small box, maybe you could hard code or infer from a model that small implies something about your policy that you should move more slowly or maybe use smaller motions. That I would believe can start falling out of like stuff like RT2 where they've actually got a load of data to do the fine tuning. I bet RT2 ends up seeing a little bit of this behavior, but somebody would have to do the analysis and find out, which would mean they need the model and it's closed source. So. They are, you can think about them in the planning domain as single step planned recovery behavior. So they're basically saying like, you're assuming basically partial access to the state of the world at planning time and then full access to the state at execution time. So it's saying I'll check the state and there's two different things I should do depending on the state. So for example, I will either open the microwave or I'll put the salmon in. And I have to check the state of the world to see if the microwave is closed first. And I assume that when I get there, I'll be able to tell. Does that make sense? So there's sort of like one-step recovery behaviors for the state that you will be able to observe but can't observe at open loop planning time. Does that make sense?
And like, what do you think might happen, like if you allow API access to like functions that interface with the word, so add the planner as one of the functions. So which kind of allows for like some sort of open loop behavior where
Yeah.
under these conditions choose to replan.
I think this is really fun. It's something I have had some like summer REU students poke around with. It's hard, but it is a fun idea. The basic idea, to both repeat the question and also advertise that I think this is cool and somebody should do it, but obviously it's not me. I mean, maybe we will, is planners are expensive. Running a planner can be expensive if the domain is really big, but also you can reliably get from A to B. But it's a robot, so the grasping won't always actually succeed. You actually probably do need to do closed loop planning. How do you replan if you suddenly fail? The language model inference is actually quite fast, even if it's not robust. So one fun pipeline would be do an open loop plan with a proper planner, have the robot running around, and then it, like my go-to example is from one of our data sets from Teach, if you all know it, where like a person is trying to fill a pot with water and they discover that in this particular kitchen in the simulation, the pots won't fit in the sink because they're too big. And as a person, they just replan. And I suspect a language model could do the replanning too. I bet you could give some kind of carefully engineered prompt that's like, you want to fill a pot with water, but the pot is too deep to fit in the sink. What do you do? And it would be like, use a cup to fill the cup with water and pour the water in, which is what the person ended up doing. But I bet you could do that. And then you could go back to your robust PDDL plan after you've like used the language model to patch it real fast when something failed. That'd be cool. It's hard. I couldn't get my REU student to do it, so you know, you do it.
I think we'll stop there.